This talk has basically two titles. One is how advances in science are made, and the other is how science changes our lives. And so I've gone back a long time. This is Nicholas Copernicus. He was born on 19th of February, 1473, so that was before probably any of us was born. Understatement for sure. But in fact, Copernicus was the person that first realized that it wasn't the sun that went around the earth, but rather it was all the planets went around the sun. So that was, in fact, one couldn't make a loaf of bread using that information, but in fact it really literally changed the way we thought about our part of the universe that we are inhabiting. Of course, Galileo actually supported this solar-centric model of the solar system, but he also did a lot of work in improving the telescope and actually then using the telescope to discover the first and largest moons of Jupiter. So these are people who, you know, laid the basis for what we call modern science today. I love postage stamps, and I think this is actually a French, yes, you can see it's a French postage stamp, but in fact, the person they're celebrating is Sir Isaac Newton. Anyway, so Isaac Newton was born on the 4th of January, 1643, and died in March 1727. Oh, I would say, but it's true, that we perhaps owe Sir Isaac Newton more than any other early scientist. He developed the mathematics of calculus to understand particle motion and the idea of a gravitational field, thus explaining the motion of the planets. I mean, this is just remarkable work. It's too bad people don't live forever. So this is James Watt. Now, James Watt wasn't really a scientist. He was an inventor. And he used the science of heat, thermodynamics, in order to create heat engines, steam engines, which were vastly, well, a factor of 4 more efficient in terms of converting heat into mechanical energy. And so this is one of his heat engines. This is supposedly a picture of James Watt when he was a child. So he's playing at the dinner table. So if any of you have children that plays at the dinner table, keep in mind that you might have a James Watt on your hands. Okay, the trouble with steam engines back in those days is that the heat was provided by burning coal, and coal is never been a very clean source of heat. So this is billowing smoke coming from 2 rather high smokestacks, but in fact, I think London as a typical example of a city which was befouled with the products of burning coal for many, many years. And you know, it's not just carbon dioxide which goes in the atmosphere. Coal has a lot of other things, trace amounts of mercury and other things that you really don't want to be breathing in. And that's still true to this day, but in fact, this is one of the things that we basically have inherited, I suppose, from James Watt, and it's difficult to entirely get rid of the pollution caused by burning coal. The other thing, however, that happens when you burn coal, or almost anything else. So this is looking over the last 1,000 years, and this is the temperature, and there are fluctuations, and don't ask me how one measures the temperature, but in fact, there were actually some very good ways of looking at isotopes and things like that. And then starting about 150 years ago, the average temperature of oceans started rising. Here we show the CO2 concentration, which one can get by looking at bubbles in the Antarctic. And again, there are fluctuations, but in fact, at about the same point, in fact, the CO2 level in the atmosphere started rising very rapidly. Neither one of these things are very good news. The bottom line is, in fact, oceans have started warming, and the fear is, in fact, that this CO2 will stay in our environment for thousands of years. And so what we do today will have an impact not just on our children, but on our children's children's children. So I think it's very important that we take this seriously. Okay, well, so now we're going back in time, I suppose. I wanted to talk about a bunch of advances in science, or at least fields of science, that have actually done something wonderful for mankind. I would not say that the teeth of this dinosaur was something that was wonderful, but paleontology really, which is the study of bones of animals that lived millions of years ago, really gives us some sense for where we are as a people on a planet and what the history of that planet is. And I think it's very important that we do this sort of thing. We like to think of ourselves as owning the earth, but in fact, it is not just ours. It's ours to give our children and our children's children, etc., on into the future. So life on Earth and our place in the cosmos, the study of fossil remains of animals and plants that lived millions of years ago provides us with an understanding of the history of life on our planet. This is a story which helps us to better understand the origins and evolution of life on Earth and also to appreciate the complex processes that produce the human race. This is one of my great heroes, James Clerk Maxwell. What Maxwell did was kind of interesting. The equations that described electricity and magnetism were pretty well established, but Maxwell realized there was one term that was missing, and when he put that term back in, what he found was, in fact, that electromagnetic waves would propagate in space and time. And now we understand that, in fact, electromagnetic waves include radio waves, microwaves, light, X-rays, and gamma rays. And that understanding really resulted from James Clerk Maxwell. This is another one of my heroes, I dare say. This is, of course, Charles Darwin, who visited the Galapagos Islands in 1835, and it was there that he developed his theory of natural selection, and ultimately wrote The Origin of the Species, published in 1859. And so another one of these people that I think had ideas which have really changed the way we thought about our place in the cosmos. This is another one some of you may think is more important. This is Alexander Fleming. He was born in 1881, and in 1928 he discovered penicillin. Now, specifically what he did, he didn't invent penicillin. What he found, it was growing in a Petri dish, and as a result of the presence of the penicillin notatum, nothing else could grow there. And so that in fact made penicillin a very useful drug to counter disease, of course. Now, I put down on the bottom here, I've never been one that makes everything look like it's all good. Healthcare in the United States now costs $2.4 trillion. That was back in 2007, so it must be up to $2.6 trillion by now. It's a very expensive business. But in fact, we do have the possibility of prolonging life. So this is another one, and this is actually a very interesting story. This, of course, is the double helix DNA. This is where all of the genetic material in our bodies is, and how it needs to be, what it needs to generate, what pieces of this information one needs in order to build a human being. So this Nobel Prize, this work was given in physiology or medicine in 1962 to James Watson, Francis Crick, and Maurice Wilkins. Now, there was another person involved in this, and I wonder, does anyone here know who it was? Okay, good. I'm glad to know that she hasn't been forgotten. So this is Rosalind Franklin here. Rosalind Franklin actually did the X-ray crystallography on DNA that showed that it had this double helical structure. Sadly, they took them so long to give the Nobel Prize that she died before the prize was given. She was a young woman still when she died, and I think she definitely deserved to share the Nobel Prize. We're almost done here, but now we're getting to some pieces of work that I think have really changed our lives. This is the invention of the transistor in 1947. And the story is very interesting because AT&T, the telephone people, realized that the rate of growth of the number of electron tubes that they needed in order to run the telephone system was getting out of hand to the point where they literally didn't have the money just to keep the tubes going. And so they went to John Bardeen, who was a brilliant theorist, condensed matter theorist, and suggested, I guess it was Bardeen and Shockley mostly, that they try to make an equivalent to an electron tube, but using semiconductor devices. And this is the first, it's sort of a bipolar transistor, but it's a sort of a weird mix of things. So as a result of the transistor, of course, rather than having this elegant telephone circa 1950, we have Apple iPhone Gs and things like that. Everyone has a cell phone of some sort right now, and it's thanks to Bardeen, Bratton, and Shockley. This is my computer. It's sitting over there on the desk, but it's basically 2.93 gigahertz Intel dual core processor, 8 gigabytes of RAM. I think the thing is lagged behind is hard drives. It's only half a terabyte hard drive, but that's usually enough for most of what I do. Okay, so now let's leave the planet for a minute. This is, in fact, the Hubble Space Telescope, which was launched April 24th, 1990. And really, you're up above the atmosphere. This is an extremely good telescope. And we can literally see more with this telescope than with probably all the other telescopes that have been put together over the years. Another interesting one is that NASA puts up satellites that don't look up and out of the Earth's sphere, but rather look down at the Earth. So this is one that's monitoring the CO2 content in our atmosphere. And the news has generally not been very good in that regard. We have too much CO2 in our atmosphere. This, of course, is Mars, and of course, I don't think there's anyone whose imagination was not captured by Spirit and Opportunity when those two Mars rovers landed on Mars. Mars is, I would say, the planet other than the Earth, which is potentially habitable, but I personally don't think it's likely that we're going to be habiting Mars anytime soon. So I just wanted to remind you, I think this is the last slide. I was actually on the board that investigated the Columbia shuttle accident. And you look at this picture of a launch, I don't know which orbiter this was, but the solid rocket boosters, each one of these guys has 3 million pounds of thrust. The tubes themselves are 12 feet in diameter. It's a phenomenal technology was built up. The main engines on the orbiter burn oxygen and hydrogen. But this guy, because of the fact that the orbiter itself weighs so much, 220,000 pounds, I would say this was not a mechanical or a technical defect. This was a defect in NASA's management. I was on the board, and it was really sad. All right, and now I'm going to slowly go through this, and you'll see there's a little piece that popped up right there. That's a piece of foam. This stuff is 1/30th the density of water, very low density foam. And now we keep going, and it looks like it's going higher, but it's actually not. It's just the perspective. It goes underneath the left wing of Columbia, and then you see a bunch of spray coming out. Obviously, it struck something. And the question was, did it strike the leading edge of the left wing of Columbia, or did it strike the underside of the left wing of Columbia? And if it struck the leading edge of the left wing, that would probably mean that the astronauts would die on re-entry from orbit. Okay, so this is it, and I wanted to show you get back to nature and enjoy the tall trees. Thank you very much.
Thank you. There'll be a question and answer session.
Professor Osheroff, may I ask for your opinions? We seem to be concerned about the planet and mankind. But you as researcher and scientists, you are working in the laboratories. What comes first, safety or the planet?
Well, okay, I think that safety and the planet go hand in hand, which is to say that I think if we abuse the planet, I think we are really abusing our future. And I dare say if I were a young person today, I would certainly be very happy to picket coal-fired. So I think it's a difficult question. And part of it, I think, gets back to the fact that the human beings have an enormous thirst for energy, and we seem to have a rather callous disregard for the well-being of the planet. Thank you for your question.
I have a question. You have mentioned many heroes, scientific heroes like James Watt, Maxwell, Copernicus. My question is, when did you start having them as a hero, and how their work affect your inspiration in scientific careers?
Yeah.
Thank you.
Yeah, this is interesting. I mean, I never thought of these people and realized that they had exciting lives and they'd made important contributions to mankind. And I suppose that as a scientist, I might have the opportunities to do that myself. But in fact, I actually did science because I derived a great deal of pleasure out of tricking nature into giving up her secrets. And this is what William Hawke, my chemistry teacher, said basically, that every time you do an experiment, you're asking a question of nature. And so when I think about doing experiments, what I think about is tricking nature into giving up her secrets by asking the right questions. And it's a lot of fun, but it really depends on who you are. I mean, I just love coming up with new ways of doing things, and I think a lot of physicists anyway do that. I can't speak for other disciplines, but I think for a lot of us, we're sort of, I think scientists in general tend to be fairly creative, and it's fun with trying to come up with new ways of getting nature to answer your questions so that you can understand what she's saying. Thank you.
Thank you very much.
Earlier you mentioned you compared research to like asking questions to nature. I was just wondering, as a scientist, do you think that there are some questions that we as humans, perhaps about the universe or existence, that we simply cannot answer? And if so, what do you think those questions are?
Well, I think there are the questions that we can't answer now. I mean, I don't know if that will always be the case, but for instance, I think our idea of what the cosmos is and how far out it goes and all that is, I think, changing as we get more information. And so, I don't like to think of science as something that's done and then it's sitting there cast in stone. In fact, it's a process of our learning about nature, learning about the cosmos and our environment and the oceans and all of these things. And I don't think it's likely that we'll ever run out of questions to ask. I guess I'm more concerned, in fact, about the quality of the answers that we get. But thank you very much for your question.
Thank you.